Okay, so last time we saw some union find data structures, and today we will see max flow min cut, hopefully. क्लास में आया नहीं कि लोग बहाना स्टार्ट कर देते हैं, क्या मसला है? Okay, so what we saw last time was data structure to maintain disjoint sets, which was basically that every time you had some universe and you were trying to maintain some partition of these sets, and the basic set of operation which we had was like find an element, which just meant that for every set we had a leader. Okay, set had a leader, and whenever I say find x, we needed to return a leader of the set containing x. Okay, so that was the first purpose of find of x. And we had another operation called make set, which was basically was creating a single node and making a loop. And the way we were keeping these things was like a reverse binary tree, right? So every node was pointing to its unique parent, and the root or the leader was parent of itself. Okay, and so another operation was union operation. So what was union of xy? It means you needed to give find x returned you some x bar, y bar was find y, and what you did is that applying some applied some heuristics, okay, and made x bar point to y bar or y bar point to x bar, right? So this is all that we are doing. So if we had two trees, right, say x bar is here and here is a tree, y bar is here is a tree, then all we did is that we made x bar a children of y bar, or rather y bar becomes parent of x bar, or the other way around, depending on this. Now here we applied different set of heuristics. So one heuristic was, so let's look at the kind of operations we did and the kind of heuristics we applied and the kind of results we obtained. So we had make set, one operation, then we had find x, okay, and we had union xy, right? So these are the operations we had, and we said, well, let's do the union, okay, do union by size. Okay, so this was first thing. What I mean by union by size? So I look at the tree which has a small set of nodes. I make the leader of that point to the set which contains the more number of nodes, and if they were equal, we didn't care. We just made one of them parent to the other. And we saw that because of this, make set always takes order 1 time, and we were talking about how much time does it takes if we have n nodes and m operations, okay, and we were interested in amortized analysis, which just means that some total time divided by m. right? So how much amount of time do I take if I perform m set of operation, then I look at the total time and total time I have taken over all these operations and divide by the number of operation to get time, okay? But makes it actually, it will take order 1 even in the worst case. It will never take more than that irrespective of what it is, okay? So it's not even, right? Find of x, because we are able to maintain that the trees are logarithmic depth, right? Actually not even amortized analysis. In the worst case, it is going to take order log n steps. Okay. Same with union xi. What is union xy? We have to find the leader of x, leader of y. So this is like two find operations. So 2 order log n and just making one pointer to the root. And this, so this will also take order log n. So basically, this is in worst case. Okay. Then we had second heuristic where we said union by rank. So rank was more like a height, but it had its own set of properties, okay, and union by rank, okay. So what we did, looked at the root of x and y, whichever had the smaller rank, we made him a child of the root of the other guy, okay, or child of the parent who had the higher root or the root value. Makes it still takes order 1 time, but again we were able to maintain the fact that the trees have logarithmic depth and hence all these operations takes order log n time. Okay, okay, worst case. And then we came up with this nice heuristic which is called path compression. So what was path compression? So path compression was, so path compression was, so suppose I have some node, okay, and here's my, say, x, here is my big tree, A, B, Z, okay, for example, and you asked me to find x, it means what do I need to do? I need to return Z, right? Because that guy is the leader of this tree. Now what I do, I said, well, I'm anyway going to do certain amount of work, right? And what is that certain amount of work? I'm going to, so you told me where x is, I'm going to look at his parent, until I find a vertex or a node who is a parent to itself. And I know that's a unique vertex in the tree, which is basically the root or the leader of the node. Okay? But I say, look, I'm anyway going to do so much of pointer chasing, then when I'm doing this, why not let me do some more amount of work and do this amount of work so that in future, people who have to find some things will become cheaper or easier. Okay? So how did this tree look like when I applied this transformation? So when I applied this transformation, this tree looked like Z remains Z, but now B is anyway, like I started with X. I said, oh, I'm going to be, why shouldn't I make myself direct child of Z? So what it does is the following. So this guy will become X, looks at him and his tree hanging from him. So I have taken this tree and made him direct child. Like I just made this pointer point to not A anymore, just like a pointer manipulation. Now this pointer has been moved from A to Z. Similarly, now what does A does? I said, okay, fine. Now no more this pointer exists because this pointer has, it looks, oh, now I should also make job easier for other people or even for myself because you might ask for me again, right? So let me point this pointer, let me make my parent not B, but let me make my parent again to Z. So what will happen then? Here I will have A here, okay, and subtree below him, okay. So this is also pointing to this, but now when I reach to B, he is anyway child of Z, so he doesn't do anything. So what is left after this is a B here, and right. So this is what the structure starts to look like, okay. Now, so this is what I meant by path compression. But now notice what happens because of the path compression. Next time, if you ask me for A, right? Now I'm not going to take more than just order 1 operation to find this, right? So all the vertices on this path, right, has made sure that in future if you're trying to find them, or in future if you're going to have a union with respect to do these things, then the amount of time which I'm going to take is constant. So I have done lots of hard work now, but for future references or for future operations, I'm going to take constant amount of time, right? Now, clearly, as we saw last time, when you do this modification, rank is preserved, so definitely all these upper bounds holds, right? But the point, so what do I do? So now this is called union by rank plus find with path compression, okay? So clearly making set still takes order 1 time, but what about find and union, right? Do they still take, right? In worst case, they can still take order log n time, but what about amortized analysis? Okay, so this is what we saw, that actually this takes order log star n, where this takes order log star n, order log star n. And what is order log star n? We defined last time what was order log star n. The log star n was, so this is how it is defined. Okay, so how did we define log star n? So we define log star n is 1 if n is less than equal to 2 or 1, whatever you want to say, doesn't matter, and it is 1 plus log of log star n. Okay, sorry, log star of log n, okay, for otherwise. So basically, what is this log star? Number of times we take log before we reach 1. This is basically what it is. Okay? So this is a very, very small growing function. Okay? And how did we prove this? We proved this using the following set of ideas. It's very important. So I'm going to rub this. First of all, for our proof, we introduced 2 operations. We said, hey, let's generalize this notion of compression to what I call compress between 2 things. So up until now, what was compression? So compression was like, okay, compression x just meant that you look at from the path from x to the root and make everybody from the root to the path, right? Every vertex from root to path, like change the pointer for every vertex from root to path directly to the root. That was the whole idea. So people, just to analyze this algorithm, people came up with, fine, let's define xy. So y may not be the root. And whenever you say compression xy, you meant that, look, start from x, go till y is your ancestor, and compress everything. So make parent of y, make parent of y, make every vertex from root to path directly to the root. That was the whole idea. So people, just to analyze this algorithm, people came up with, fine, let's define xy. So y may not be the root. And whenever you say compression xy, you meant that, look, start from x, go till y is your ancestor, and compress everything. So make parent of y as your, what you call, as your parent for everybody up until y. Okay, so example was like, for example, look at this path. Okay, just for this, and suppose I gave you, suppose this is x and this, suppose this is y and this is x. Okay, now what I'm trying to tell you, well, when you are trying to compress x to y, take everything and modify this to here like this. This guy is not going to, like, x parent is not going to be him, but x parent is going to be the parent of y. Great. So now I go here and I make x here and I make this. Now let's call this a or something. Fine. Now what will I do with a? I will do the same with a. Okay, this is it. So here is a, directly looking at the parent of, and what will y do? Y is anyway looking at him, so this is y, right? So this is what I meant, that you compress between x and y, right? And we said, and we introduced another operation called scratch, sorry, shatter. And what was shatter? Okay, so what was the operation called shatter? Basically, you went from somewhere to somewhere. For example, if I do shatter from x to y, right? What will I do? Shatter from x to y. I go from x to y on this path and make x parent of itself, y parent of itself, and so on and so forth. A parent of itself, so forth. Okay, so this is what we did. The intuition was, and then we try to show the following. We said that given any sequence of operation, C, which consists of find set, union, and what was that called? Make set. Okay, let's first forget the make set, because they are only going to give us order n, because we are only going to do this. And we said, let's forget union, because union, once I gave you the leader, it just takes order 1 operation. So replace that union with just 2 find set, right? And that's good enough for us. Now the idea was that then we defined the notion of, okay, look at your set of operation, and we cut down, we said, hey, let's look at all the operations which has rank S, and look at all the operations, all the vertices which has rank below. And what did we to cut up as log R? So all these are way much smaller, but here are all those people whose rank is between S, S minus 1, dot, 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 log R. Right? Sorry, log, huh? R and R. Okay? So R minus 1. So like most people mass was here. But what did we able to show? That if you are going to give me things here, I'm going to take really very much small amount of time, like order n in worst case. And then we came up with this beautiful recurrence. And the reason why I'm trying to bring this up again is that we had this T, M, and R. What was, suppose, what was this T, M, and R? We are going to do M operation on n node tree, whose rank is at most R. We use this as the base case, NR. But using this as a base case and divide and conquer approach, we were able to show that T, M, and R is less than equal to, if you recall correctly, what it was? But that gave us a lower bound on T, M, and upper bound on T, M, and R. What was that? Okay, we were able to show this is equal to m plus 2n log star n times r. What I'm writing, log star r rank. So we use this as a lower bound, but now we have much better lower bound. So if you plug in that lower bound, you will start to get you start to cut not at log r, but you will say let's cut at log r. You will get a better bound. Then you will start to cut at log r. And this is how you can prove and replace this not by log star n, but something called Ackermann function of n, which is even much slow growing function than log star n or iterative logarithm. But I'm not going to give you the proof. But all I wanted to tell you is that the proof just comes. I take the same template of the proof and I use better and better lower bound in my divide and conquer. Like so, each iteration gives me a better lower bound. I bootstrap this new layer bound to get a better lower bound. I bootstrap that to get even better layer bound, and whatever the end you get is what is called Ackermann function, and that's the best known currently. Okay, so what I gave you is only log star n, which is a very good very good already, but you can do much better than that. Okay, and the proof is very much similar. So if you look at the paper which I send you, it will give you that proof. Okay. So that's all that I wanted to talk with respect to what is that called? The union find data structure. And now we will move to what is called like slightly graph theoretic, slightly algorithmic, right? And what is called max flow min cut. Okay, so let's do some max flow min cut. Okay. So what we are going to talk about now is what is called max flow min cut. Okay. Max flow min cut. Have you people seen max flow? No? In graph theory, did you learn max flow min cut? Okay. Okay. So if you recall correctly, we defined the notion, given a graph G equal to V comma A, right? We defined the notion of cut. What was cut? Was basically a partition of vertex set into two parts. Okay. So here it's some S, here it's V minus S, right? So this partition is called cut. Have people done global min cut? No. No. Deleting minimum number of edges to disconnect graph. Have you learned this? Like in the course, in this course. Okay, fine. Then I will not get to that. Okay. So there is also a notion of what is called global min cut. Okay. So there are few notions. Global min cut. Okay. So what is a global min cut? Okay. Input is undirected graph. Okay, G, and the question is find the minimum number of edges whose deletion disconnects the graph. Okay? Do you know how to test whether a graph has a min cut of size 1? Right. Do you know how to check? Yes.
Hello, can you hear us?
Yes. Do you know how to find a min cut of size 1?
If the graph has a bridge edge,
Yes. And
then I think
yeah. But and how do you find a bridge?
TSS.
Okay, good. But maybe there is no bridge, but there's still you can delete minimum number of edges to make the graph disconnected. Can you give me a lower bound on min cut of a graph? Suppose I told you a graph has a vertex of degree 10. Is there a lower bound, upper bound on the min cut of the graph? Do you see this question? Suppose G has a vertex of degree at most 10. Then can you give me an upper bound on global min cut?
Minimum degree of the graph. Minimum degree of
So can I say it is at most 10?
yes.
Okay. But it may not be true all the time. Okay? So what we would like to solve is, say suppose, so this is one way of, this is global min cut. But suppose now I give you undirected graph G, or maybe, okay, so first let's try to understand undirected graph G. Okay, so this is global min cut. Okay, now I'm going to define the notion of what is called ST min cut. Okay, input could be undirected or directed. Okay, and question, find the minimum number of edges such that there is no path from S to T. Okay, so I want to delete minimum number of edges so that there is no path from S to T. So notice that in undirected graph, if graph G is undirected, it definitely means that after, so suppose if it's such an edge set. Okay, what is the property of such an F and edge set? What can you say about G minus F? Suppose it is undirected graph. Okay, undirected graph. Can you say something about G minus F? Can this graph be connected?
No.
Good. So first of all, notice that this there are two properties. G minus F is disconnected and no connected component contains S and T, right? So after I delete, I might have many components. There will be one component which contains S and there's another component which contains T. Because if S and T were in the same connected component, it implies there's a path from S to T. So your F, which is going across these black edges, cannot be a cut edges like this, like this, like this. This cannot be, right? Okay, so suppose I give you an algorithm for min cut. Okay, suppose I give you an algorithm for now a polynomial time algorithm. Suppose I give you an algorithm for ST min cut in undirected graph. Can you give me a global min cut? Do you understand my question? Suppose as a black box, I give you an algorithm for ST min cut, which runs in time, say, order n to the power alpha, okay, to find ST min cut. Give me an algorithm to design global min cut.
Of course, just calculate the escape cut for all pairs X power T.
Yes.
And then table OS, that should be the
Global min cut.
global.
Exactly. So definitely global min cut looks like an easier problem compared to ST min cut, because in global min cut I don't care which pair of vertices you cut, but in ST min cut I do care which pair of vertices you cut by deleting edges. So you're right, you can do it in n to the power alpha plus 2 because there are only n square pairs. Find min cut for every one, take the one with the minimum number of edges. Good. Okay. But suppose now I have to think, so we will try to do an algorithm for min cut, okay? Okay. But so let's try to understand the concept. Suppose F, like, look, all I am telling you that input is undirected or directed graph. Suppose now that input is a directed graph, and find the minimum number of edges such that minimum number of edges such that there is no path from S to T after deleting these edges. Okay? Now I am asking a question. Suppose F is such an edge set in D, a directed graph. How can this structure will look like? Okay, let S be all the vertices. Okay, consider D minus F. Okay, I have deleted all the edges that belongs to F. All the vertices that are reachable from S, okay, reachable from S in D minus F. Okay, question number 1. Can T belong to S? Good. Okay, so look at S and look at here V minus S. Okay, what is the property? The property is S is here and T must be outside. And what else is the property? Can there be an edge like this? Because then every vertex here is reachable from S, then I could have reached this vertex using this edge. But nobody prevents us from having an edge like this, right? And maybe there are no edges, but in a directed graph, you could have an edge from V minus S to S, right? So this is how the structure of min cut, or any cut for that matter, which disconnects any F, okay? Any F that disconnects S from T has this kind of structure. If you look at T minus F, look at the reachable set of S and remaining, there cannot be an edge going from S side to this, and S, capital S contains S and the remaining guy contains T. Okay, so this is what ST min cut means. Okay. Okay. So our whole idea is to design an algorithm solve this problem. And to solve this problem, like there are many ways of doing this, but to solve this problem, we are going to develop this whole theory of max flow min cut. Okay? Okay. So now I have told you the motivation. What is the combinatorial problem you would like to solve? And to solve this problem in polynomial time, we will develop some theory. Okay? Okay. So what are we going to assume? Okay. So let's draw some example, okay? And we will leave this example, okay? Okay. So we are given a directed graph, okay? We are given a directed graph like this, and let's say it's some other edge left. Okay. Okay. So we will always be given a directed graph or network, okay, or network, whatever you want to call it, D, and every edge has a capacity. Like think of this as like a your city and the pipeline of your city, like water pipeline, right? So maybe there are some places where there is a very big pipeline, like pipeline with huge capacity is going on, and then it might be coming out from there a small pipelines with different capacities. So to model this flow kind of things, like we would like to flow things around, but under the constraint that you cannot overflow. So we have to define some sort of capacity for every edge. Okay. So the first object which we need to define is a notion of capacity. Okay. So what is the capacity? Capacity will be function from E r greater than equal to 0. This is what capacity will be. For example, let's write down the capacities here. So for example, this is 4, this is 2, this is 2, this is say 6, some number. Like it's some assignment of edges to some positive reals. Okay. In my case, I've just taken integers because this is slightly easier to manipulate for an example, but there's no reason to believe that. Okay, so this is what is called capacity. And for edges, so if E is not in E, we more or less assume that capacity of such edges are 0, like they do not exist. So we will assume that capacity is S. And what is a flow? Flow is also a function from edges to real number. Okay? So what is my flow? So this is a capacity function. Now I'm going to define a flow function. What is my flow function? Flow is also from E to R greater than equal to 0. So flow is also a positive quantity. Okay? And what should be the natural constraint on flow? Look, it should not overflow, right? So what should you assume? That flow of E is less than capacity of E, natural constraint, right? So this is a natural constraint. Like you cannot flow more than what is your capacity, right? So this is a natural constraint on the flow. Secondly, we will always assume that the flow is 0, right? Flow is 0. Okay. Okay. Another thing, if your network things are flowing properly, then what happens? Whatever flows to a node should go out from there. Like, so amount of flow which goes into a node should go out of that particular node until we have leakage and this and that. But let's assume that we are in a very perfect condition. Whatever comes in goes out, right? So this is what is called conservation of flow. Okay. So for every vertex, V in V minus S comma T, I'll come back to S and T, they are special vertices, okay. What happens is that flow in is flow out, okay. So let's denote by this summation over U, F flow into UV, right. So fix a vertex V, right. These are the guys which are going out, right. So flow into V should be equal to summation over flow out of V, right. So what should we do here? W flow from V to W, that's it, right. So this is what is called conservation of flow. Okay. And what is the flow value? Given a function f, what is the flow value? What is the flow value? It is defined as, so I define flow as, basically think of this, so in most books they will assume that source has no incoming arcs, okay. Most books assume the following, but let's not assume that for our purposes. What do they assume? What is source? No incoming arcs, okay. And for T, it's like this is what is called source, and T, which is called sink, no outgoing arcs, okay. But we will be slightly offhand and we will assume that it's just a normal directed graph. But then what will we use? The flow value to be equal to so this is called flow is nothing but total net flow out of S. Okay. So what is the total flow net flow out of S? Is basically sum over, okay, S to W flow out of S, right, not flow entering into S. So over W flow from S to W minus flow which is coming into this, okay. Right? So this is what is called total net flow out of S. So as I told you, most books assume that S has no incoming arcs, so this will become 0. right? And what does conservation of flow will imply? Conservation of flow will imply that this quantity is equal to flow into T. Okay. So this is what I will define flow. Okay, forget about T. Okay, so this is what my definition of net flow out of S means. So now just to make the notation simplification, let's use a notation which I'm going to use for any vertex V. For any vertex V, I'm going to define the notion of total net flow out of V. For any vertex V, total net flow out of V, I'm going to define as, okay, yes,
So the flow value will always be zero, right?
flow value,
Will always be zero, right?
why?
So are we assuming that conservation of flow is there?
I told you for every vertex V in V minus S comma T. Okay, so in most book they assume that this is like this part doesn't even exist because there is no income omega, but for many computation and calculation it is better to think that there is something and what I'm computing is just a net flow which is going out. So it's just S and T which is allowed to have like unbalanced flow, but if, like without flow conservation, but every other vertex except S and T has to satisfy the conservation of flow. Okay. So what is the delta of V? This is basically for any vertex total net flow out of V. So which is same as, I can just write down this summation U F U comma V minus W F V comma W. So if you want, we can assume that S and T has no arcs, if that helps. Okay, so maybe it will not confuse you much. Okay, so or let's see. Now let's sum the net flow out of everybody. What will happen? So what will be summation V delta FV, V in V. What will be this equal to? Notice that for every vertex except S and T, net flow is 0 because of flow conservation. Right? Because this equal to this, so this minus this is equal to 0. So if I do this sum, then this is all I'm going to get is delta F of S plus delta F of T. So what does this implies? So what do we know from here? What does this imply? It implies that if you notice, what is the cardinality of F? Is delta of F of S. Do you agree? This is what it is, right? So if I substitute here delta F S, what do we get from here? Can I say the following? Look, flow is delta of F of S, which is equal to minus F of T. Yes?
That would imply delta F S plus delta F of T is equal to zero.
Yes. No, there like delta f of s is equal to delta f of t minus delta f of t. So there is something going out of s of, what did I define? Look, summation of f of s is not sum of these two things, it is just the one quantity. So there is always something going in. Okay. Okay. So I hope this is clear to you. Okay. So now, okay. Yes. Yes. This is 0.
No, wouldn't that give a negative value to whatever, like the source? Because you have taken that quantity earlier. You were going into.
Look, let's just sum this up. Just delta f of v is summation over, no, you're talking about this or you're talking about this?
I'm talking about just say the source. So for the source, the total net
Source we have another.
okay.
What? This is what it is for source, no? It's the same definition. I don't understand what's the problem.
The sign.
Sign. So if we take the second definition for the source, then
Oh.
from somewhere to source it would.
Yeah, no, but this is what it is. Whatever is coming into it. Okay.
Excuse me, sir.
Yes.
Yeah, so we have assumed that delta f of s is equal to minus delta f of t.
I did not assume it, I proved it.
So, sorry, then why can't we just connect s and t?
Okay.
And the flow between that connection is delta f of s. Then we can assume every vertex to be to have conservation of flow.
We could. Okay. So I do not want to make you people confused anymore. So let's assume that S has no incoming arcs. Okay. So this is this. Okay. Just to make your life easier. Okay. Otherwise, okay, fine. But this is perfectly okay. Now if I sum this up, what will we get? What are we going to get from here? So now I don't even have a definition of delta f of v, right? So notice what is the flow going into this network is basically what is coming out of W, right? And now everywhere it is conservation of energy, like conservation of flow. So what is the flow going into T is exactly what is going out of S, right? So you could also define flow is equal to summation say V F V to T. Okay. Okay. So now what I want to talk about, like couple of concepts about, not concepts, couple of definition. Okay. So what do we call? I said F, the flow, is feasible. F is feasible if first is satisfied, or rather flow of, for all E, flow of E is greater than or equal to 0, less than or equal to capacity. Then we say this flow is feasible. Okay. People also use the following terminology. Okay. F saturates an edge E if f of E equal to C of E. So like flow is equal to the capacity. Then we will call it that it is saturated, and avoids edge E if f of E is equal to 0. So it is avoiding this edge because it is not sending any flow through it. Okay. And what is the maximum flow problem? The maximum flow problem is to find a flow with the maximum value. Okay. So what is the maximum flow problem? Okay. So what is the maximum flow problem? what is the max flow problem? Given d, s, t and capacity function, find f with maximum f value. That's it. So you want to find a flow function which maximizes some things which are going out of this. Okay, so that is our goal. Okay, so for example, so given this set of constraints, I can come up with some flow function, right? For example, so whatever I do not write, please assume that for those as if my flow function gives 0. Okay, so for example, I make flow 4 here, okay, and I make 2 go from here, 2 go from here, okay, and then this 2, no, okay, this is 2, I want to, so whatever black is what I'm assigning my flow function to be, 1, 1, 2, this is fine, 4 went in, 4 came out. Now 1 has gone in and like either it can go from here or it can go from here. So suppose he goes from here, so flow in is flow out, and now two things are going in, so either he can go via like this or he can go 2 like this, because he had a, so he went to 2 with this, now he has a 2 here, he went with 2 here, right? So this is a flow, but what is the value of this flow? 4. But I know this example of flow is pretty wasteful. We are not utilizing the capacities very well, right? We could have done something slightly very differently in the sense, let's look at this. It's wasteful, just for an example. Okay, so what I do, I let 4 go from here, 2 go from here, 2 go from here, okay, or say y2. I can take 5 from here, but now look here, the only way to go out is this, but it has a capacity 10, so 5 can definitely flow out of him, right? But now if 5 flows out of him, only 4 can go here, right? So like somehow he has to distribute between this, so suppose he distributes 4 and 1 here, right? So now 1 has reached here, 3 has reached here, so now what can he do? 4 has gone here. Now let's say he doesn't send anything in 3 here, sends 1 here, like 5, 5, 1, 2, 1, 3. I cannot send him, so send 3 here, right? So 3, 3, 6, 1, 7 has gone here, but this guy needs to send out more things, right? So 3, how much it has got? This guy, let's see, 4. So either he can saturate this completely by sending 4, let's suppose he does, okay. Now let's see what happens to us. Now 5, so this is fine. Now we have 3 here and he has a place to go, right? This is also a flow. So what is the value of this flow? 4, 4, 8 plus 3, 11, right? And my claim is this is the maximum flow, but how do we prove this? We tried some examples, that doesn't mean that this flow is maximum, right? So, okay, so this is what the notion of max flow is. I have already told you what is the min cut between S and T means. It is a partition of S into S and partition of T into T, okay? So what does max flow min cut theorem tells us? The max flow min cut theorem tells us the following. So at least let me introduce the theorem. Maybe we will be able to prove also, who knows? I have no idea. Let's see. Okay. So what does max flow min cut theorem says us? This is the famous max flow min cut theorem. What does it say? It says in every flow network, with source S and target T, the value of the max flow, okay, the value of the max flow is equal to the capacity of the min ST cut. Okay, I guess I have not defined the notion of capacity of min ST cut. Okay, so let me first define the capacity of min ST cut. Okay, so for example, so let's take an example. I have S, some node, right? So for example, or maybe this example should illustrate, okay? So what is the capacity of ST cut? Look at some place which contains S and look at the outside. Look at the edges which are leaving S and going to T, and just add the capacities. Not the flows, add the capacities. Like what is the capacity of this cut? This edge is going out. What is its capacity? 3. So add 3 plus. Is this edge going out? Yes, this edge is going out. Its capacity is 6. 6. 1 is my flow. Is this edge going out? Yes, it is. 3. Is this edge going out? No, this edge is going in. So we do not count its capacity. Is this edge going out? Yes, this edge is going out. So I count its capacity 10. Right? So given any ST cut, right, I want to find a ST cut so that if I add the sum of edges which are going across, the capacity of those, that is minimized. Right? And this is exactly analogous to what we were doing in ST cut, right? Hey, look at this edges which we deleted, right? Look at the edges which are forward, which we deleted. Only thing which is left is minimum, like going inside. So this is what I'm saying that, oh, this is an edge. Now it's like, think of this as like weighted edge cut. I want to find minimum weight edge set, which deletion gives me S and T cut, right? So I have generalized my problem from undirected to a weighted problem where given an ST, I want to find a partition of S and T such that the weight of edges with one endpoint in S and the other endpoint in T is minimized. Okay? Okay. So what is a min cut problem? Is to compute an ST cut whose capacity is as small as possible. So the minimum cut problem is to compute an ST cut with whose capacity is minimum. This is it. Right? Okay. So now let's define a notion. Okay. So, or in other words, okay. So formally, let's define the notion of cut. So we have a capacity function C from E to R greater than or equal to 0. This is our capacity function given to us. Okay. And what is a ST cut? ST cut is basically S and T. It's like S union T is V, S intersection T is empty, S is in S, and T contains T. So basically T is V minus S, our role. Okay. So So capacity of the ST cut, the capacity of a ST cut is sum of the capacities of edges that start in S and end in T. Okay, so this I can write it down. This I can write it down as, this is a notation people use. Okay, what is this equal to? If you notice, summation over V in S, summation over W in T, okay, capacity of V to W. Remember, now I am taking over all V in S and all W in T. Why? Because if there is no edge, what is its capacity? 0. Okay, so we assume if E is not in E, capacity of E is equal to 0. Okay, so with this assumption, if you notice, what gets counted? Only those edges which really are real edges and their capacity. So this is how you can define the capacity of ST cut. Okay, so now I have made formal. So now whenever I say I'm trying to find a ST cut of minimum value, means I want to find a partition of S and T where S contains S, T contains T, their intersection is empty, their union is whole vertex set, and the ST cut capacity of ST cut is minimized, right? And what does this theorem tells us? That if you give me in every flow network with source and sink, how much you can send is equal to how much you need to cut from S to T. Okay, so yes,
So we think of transpose linear programming problem.
we need not.
If we think of transpose the linear programming problem,
Yes,
will name not be equal.
yeah. It is like if you think of them as, then this is nothing but optimization. Like it's like linear programming. One is primal, other is dual. So at the optimum value, both are equal. Okay, but let's give a combinatorial proof so that we can design a combinatorial algorithm. Okay, but you are right. If you think of them as a primal dual or linear programming, then yes, one is primal, other is dual. Okay, so what do I like to prove is the following. As a preparation, okay, or maybe I will assume this lemma and try to prove this, okay, because that might be a bit more fun to do. So the lemma is, let F be any feasible, okay, let F be any feasible ST flow, okay, and let F be any feasible ST flow, and let ST be any ST cut. Okay, then what can we say? The value of F is at most this is actually obvious. What does it tells you? Hey, look at S and look at T here, right? Look at S and look at T here, right? So if I delete all this, S cannot reach T, right? So maximum amount of flow you can send from S to T is upper bounded by some of the capacities of this. Like there's nothing more happening here. Okay, of course we can formally prove this. Okay, but for now, right, it is at most, it is not saying anything more. Moreover, and this is nice, if f equal to st, if flow is equal to st, if and only if f saturates every edge in the cut, saturates every edge from S to T, and avoids every edge from T to S. But let's not prove this for now. Okay, let's try to prove Max-Flow-Minkert theorem assuming this lemma. Okay, this is not very hard to prove, it's just a manipulation. So I have less in this. So which direction here is easy to prove? Okay, which direction is easy to prove for Max-Flow-Minkert theorem? Is any direction easy to prove? Let's say f max is less than equal to min st. Okay, this is easy actually. This just follows from the first part of this, right? You look at any ST cut. So what does it tells us? Look at any ST cut. This is S and this is T. What is the flow? What is flow happening? Flow is basically, look at the edges going here and look at the capacity of this. If I delete this set of edges, there is no way I can go from S to T, right? But okay, this is not formal enough, I'll make more formal enough, okay? But what is an interesting idea is when you try to prove f max is greater than equal to min st. Okay, this is slightly more interesting to prove. Okay, and let's try to do that. Okay, at least let me introduce the idea, and then maybe we'll stop here and meet next week. Let f be any feasible flow. Okay, let f be any feasible flow. Okay, so now let's define the notion of okay. Okay, now we define the notion of what is called residual flow. Okay, now what is an intuition behind residual flow and all this business? Okay, okay, let's take an example to exemplify our construction. Okay, this is what it is, and suppose I add flows of say 4, 8, 6, 4, 8, 6, 2, 3, 2, 3. Okay, and suppose the amount which is flowing inside is like I had a very good black pen, but okay. Suppose the flows are like 3, 1, okay, 3, 1, and then I have 2, 1, 2. 2, 1, 2. So out of flow, 3 unit of flow. And now if I ask you a question, can I increase the flow here? Right? So if I look at edge 3 to 2, I know that it can send one more unit of flow. If I look at here, it tells me that I can send 7 more unit of flow. Okay? So what people do is that, like, but yeah, I mean, how do I go about finding a path along which I can increase the flow, right? It's like I know that I can increase here, but here I may not be able to increase because this is 0, because it is completely saturated. So I cannot hope to increase the flow in this direction. And maybe if I want to increase flow in some direction or along some edges, maybe we have to decrease the flow somewhere else, right? And then only we can achieve the global maximum, right? So people came up with this new definition of what is called residual flow or residual network or whatever you want to call it. Okay, so what is residual network or residual flow? So think for now it might be make easier, at least let's look at for this network. Okay, suppose this is it. So what does this tells us on this is this, we agreed on the case that okay, maybe along this edge how much more unit of flow can you send? 1 unit of flow you can send. Okay, so that's good. I write 1, right? But so let's write down everything which we can send, which is residue, which is left over. How much is left over here? 7. How much is left over here? 5. How much is left over here? 1. How much is left over here? 0. Okay, but what do we know? That look, I should also be adding some things to say that hey, we might have to reverse this edge, like reverse this. So what we do, we add some more edges to this digraph, right? And what does this represent? Oh, how much amount of flow you were sending before, that is the amount you are allowed to pull back. So what should be the residual capacity here? 3. So if you look at the sum, it says how much can I flow send in this direction and how much can I push back in this direction. So what will be this? 1. And what will be this? 2. And what will be this? 2. And this? 1. Right? And this is the graph which is called residual graph. So now let's formally define actually what we did. Okay? So what we did actually is the following definition. So you are given a feasible flow. So it's a feasible flow means it satisfies conservation, and for every edge it is greater than equal to 0 and less than equal to capacity. So how we define is as follows. So I am defining a residual capacity. So it is defined with respect to some flow f, okay, comma u comma v is equal to, suppose uv is an edge, then what did we say? If u and v is an edge in my graph, then what did we define? We defined here capacity of u comma v minus flow of u comma v. This is what I can send, right? Further, if u comma v is in edge or whatever you want to write. But suppose u and v is not an edge in my graph, then what? But suppose v comma u is in my graph. then what should be this? This is what we had, right? Here what did we add? Oh, along this edge I could push back flow of 3 if there was a flow going out from U to V of 3 and 0 otherwise. Like in all other edges, I was neither sending something nor I am pushing something back, right? So this. So the lemma or the result which you can prove is, so what does the forward edges in this graph represents? Are that amounts that is left, and backward edges are the amounts that has been used, right? So forward arcs is like amount that is left, and backward arcs amount that is used. So if I sum them up, what is that equal to? Capacity. And the lemma or the theorem which we will say, okay, which we will prove, and that is the core of everything. What can I rub? Okay. Let's rub this theorem. We don't need this. Maybe. Okay. So what is this? This is a lemma which you should try to prove yourself. Otherwise, I may will prove next time. T is not reachable from S. T is not reachable from S in GF, okay, if and only if F is a max flow. Okay. Right. So basically what this says that in your residual network, if you have a path from S to T, right, if in my residual network we have path from S to T, in residual network, then I can increase the flow. And how will you increase the flow? Very easy, very simple. I said, oh, fine. If there is a path, then all these are non-negative numbers. Let's choose, let eta equal to minimum of what you call capacities, like residual capacities on this path. Okay? Residual capacities on this path. Now, how will you define new flow? What will you do? Look, if the edge does not appear here, keep the same flow. If the edge, like now look at all those edges which appear. Now, if edge appears here, and that edge is present in my graph, what should I do? I should increase the flow by eta. But if an edge is here, but that edge may not be present in my graph, it means it tells me that I should decrease my flow. So for those F, what will I do? I will decrease the amount by eta. But notice what happened. But at the source, my flow has increased by something. So definitely I have increased the flow, right? So we'll make it formal. So the idea is very simple. You define this residual graph. You look for S to T path, and you look at your current flow. Like for example, all 0 is a good starting flow, right? Because that satisfies all the properties, right? And iteratively we will increase the flow one by one and change. So I will find this path and increase my flow. How? If an edge is not present on this path, give the same flow as the original flow. Otherwise, if the edge is present in my original graph, then I increase by eta, and if it is not present, then I decrease by eta, and that is my flow. But I have to show that this is satisfies conservation, the new flow satisfies conservation, new flow satisfies feasibility, and all these kind of conditions, right? So next time we'll try to make this algorithmic, prove this, and prove Max-Flow-Minkert theorem. Okay, so that's where. So I've given you an idea of the whole proof, but it will require more than an hour to prove this. Okay.